Then I'll share. Okay, hold on. Okay, can you see the slides? Nampak? Nampak ke slides? Nampak? 7. Okay, so let's have a look at different CVD systems. So last time I've told you that we have a few CVD systems due to the evolution of the research and findings, and scientists and engineers and industry uh, try to create or try to give a new name to a new system so that they can work on the system continuously, right? So we have AP CVD, for example, atmospheric pressure CVD. We have LP, low pressure. We have PE, plasma enhanced. We have HD, high density plasma. We also have LA laser system. We also have HW hot wire, right? So you'll probably can find, if you Google CVD system, then you'll probably find more than this stuff that I show on the slide. But the basics of the process remain the same. So it's still a CVD process. By default, CVD is a thermal decomposition process. So when we say it's thermal, and you need to run through the process, you need to run the process at high temperature. So typically 1,000 degrees C, for example, in order to initiate decomposition of the precursor gas or gases to be able to initiate the deposition on the samples. So some of these processes can also be done at lower pressure, but the plasma is, for example, the plasma is initiated by some other medium, for example, using a high voltage supply in order to initiate plasma. But the CVD itself, if you look at the default CVD, it doesn't require any plasma in the process. It's just a thermal decomposition process. In fact, if you run a CVD process in our lab, for example, you can just run high temperature with certain flow rate of your carrier gas, nitrogen, for example, and then you can use your precursor material in the form of powder, and then your sample maybe glass or maybe silicon, maybe some other stuff, sapphire or silicon carbide or other high temperature substrate, can just be placed in the front of the silicon powder, so of the silicon precursor, for example, of some other precursor material, for example, and then at that high temperature, ambient or atmospheric gas coming in and send the precursor, and that is also called CVD as well. So let's have a look at what do we have. So this is some examples of CVD reactors. So you can look at the first one or you can look at the second one. Well, the basics are the same. You need to have your tube. You need to have your heater in the form of heating coil, for example, to do the RF induction. Then you need to have your quartz board or graphite board. Then you need to have your silicon wafers if you're talking about silicon substrate for the deposition. So you need to have your gases. So in this case, you can see you have ACl, dibrane, phosphine, arsine, H2, and then you can also have some other precursors if you need the help of some other precursors. And then the system is normally what we call ended. The tube is normally ended with a vacuum, or no, with an exhaust system in order to exhaust the byproducts from the process, and then the byproducts need to be scrubbed using exhaust scrubber. Scrub is more like cleaning process before you release the byproducts into the atmosphere. So kilang kan you tengok dia punya exhaust line kan ke atas tu, dia punya cerobong tu. So before the byproducts are released into the environment, they have to be cleaned. So they have to be of certain standards before they are released to the atmosphere, or else they will cause pollution to the environment, right? So in this case, the byproducts need to be scrubbed by using exhaust scrubber in order to make sure that the byproducts are safe and clean before they are released to the environment. So for example, if you talk about LPCVD, LPCVD is a CVD system at low pressure. So if you compare to a typical CVD environment, so it's slightly at low pressure. So whatever you run in the CVD process, whatever systems you use, it normally has its own pros and cons, right? So LP, for example, is normally known at low pressure. You have to run it at low pressure, therefore the throughput is normally slightly lower if you're running CVD process at higher. Okay. Phase reaction limited low temperature, but at a high film growth velocity. So it's kind of pushing the process in order to deliver the quality, right? So solution is to run batch processing. Well, normally this is done in mass production. It has to be run in batch, or else it won't be feasible for mass production. So I won't go through this. You can just look at the process parameters for the LPCVD. Right, this is another process parameters for LPCVD as well. I'm just going to go through briefly on all the systems of CVD that we have. The second one is called PECVD, plasma enhanced CVD. So in this case, if your default process doesn't have any plasma, this CVD process requires a plasma. So when you use a plasma, your process can be run at lower temperature. Okay, when you use plasma, your process can be run at lower temperature. Any idea why is it that way? If you relate back to the definition of CVD, kenapa you rasa when you run using plasma, the process can be run at low temperature? If you compare to typical CVD process, why do you think it's possible? Any idea? To just comparing typical CVD process at high pressure to deposit silicon, for example, at 1000 degrees C. And for this particular case, PECVD, you can also do silicon deposition, but then at 200, 300 degrees C. But plasma is here in the system. So why do you think it's possible to run at low pressure with plasma? Any ideas? Any guess? Ain, ada idea Ain? Ain, Natasha? Faika, any idea? Why can we run at lower pressure? No idea, right? Anyone with ideas? Siapa lagi ada ni kat sini? Farah Azwani. Farah Azwani, any ideas? Kenapa kita boleh run at lower pressure now for a PECVD? No idea, huh? Okay, I leave it to you to search. Okay, you think what is the role? Later on, you try to search what is the role of plasma in CVD system that enables the process to be run at lower temperature. You can just compare. If you run at high temperature, why do you need the high temperature in CVD? To do thermal decomposition, right? So you still need to use thermal decomposition. You still need to have thermal decomposition in any sort of CVD system. But if you don't have pressure, you need to have something else to do the decomposition. Okay? Saya dah bagi hint. So if you look at this PECVD system, so you have electrodes on both sides, a positive side and negative side. So that's where you generate the plasma in between. So the plasma is argon based, and the plasma is generated by high voltage. You can watch the video that I've posted on Elon YouTube video though, on the generation of plasma and the setting, the gas, the parameters, the buttons and stuff. And for example, if you talk about silicon deposition, we have discussed in default CVD, we need to use silane SiH4 in order to enable silicon deposition, silicon film deposition. So okay, thin film lah. Selalu kita panggil thin film. You don't deposit thick films in CVD system. Well, you can go for like 1 or 2 microns, but hardly you deposit 50 microns or above. Even 10 microns is considered thick already for CVD system. If you go for like 100 microns or 200 microns, that's not CVD already. That's like using a piece of silicon wafer from the lab or from the industry. Okay, because usually if you look at our silicon wafer in the lab, it's like 250 micron in thickness. So it's not possible to deposit 250 micron by CVD. Might as well you just buy a wafer and you get monocrystalline some more. If you deposit using CVD, then the best you could have is usually polycrystalline. Most cases you will have amorphous silicon. Some cases where you already have epi layer at the bottom or a seed monocrystalline, then depositing a new silicon film on the seed layer will help you to have monocrystalline as well. But that might require subsequent annealing process in order to turn the polycrystalline or highly polycrystalline, close to mono but not yet mono, into perfectly monocrystalline. Okay, but most cases it's either amorphous silicon or a polycrystalline silicon. So anyone has ideas, how do you check? For example, kita tengok dekat sistem ni, you are depositing silicon now, silicon thin film, say 1 micron, and then how do you know, how do you check? Let's say you are depositing on silicon wafer, so you are now depositing polysilicon 1 micron on silicon wafer. How do you check the crystallinity of your polysilicon? From our previous topic and from your FY experience maybe, how do you check your polysilicon crystalline quality? Either it's amorphous or poly or mono. Anyone? Ilham, any ideas, Ilham? How do you check the crystalline quality of the deposited film in this case? You can unmute or can just write down. Ilham or Inas? Any ideas? How do you check the crystalline quality? XRD, yeah, that's good. XRD. Right, Ain, XRD. Did you do XRD for FYP? You buat XRD kan, you punya FYP hari tu? Right, that's good. All right, what do you see? Maybe you can share. What do you see from your XRD? For example, if you have polysilicon film in this case, so you go and measure XRD, what do you get? The peak for crystals, right? The peak for crystals. So do you, okay, if I assume my polysilicon now is polycrystalline. So do I see one peak or many peaks, or how does it look like? So anyone with XRD experience can also share. You can just type here. What do you think, Ain? Do you get to see one peak or more peaks, or how? Not sure. Okay, Roland, you say not sure. Maybe many for poly. Yes, exactly. That's good. So ni kalau XRD ya. So kita last time kita dah discuss wafer characterization, right? So and we've gone through a couple of characterization techniques, and one of the techniques that you can use is XRD. But in wafer fab we don't use XRD because normally the film quality is already pretty much fixed. So I haven't heard of any XRD system in wafer fab, but in other fabs like solar cell, I think hardly as well. For some other fab, maybe. Okay, Ilham, you said many as well. When you have polycrystalline, what does it mean by poly to begin with? Sangkut tak kat PCVD ni? Tak apa, kita discuss sekejap, it's okay. What does it mean by poly? It's many, right? Polycrystals mean many crystal. We have covered this in 386 last time. Kita tengok kan, you punya kita belajar the earliest part of 386 is like amorphous. Your assignment 1 was to draw amorphous crystalline arrangement, and there is no periodic arrangement at all. And then the second part is to draw polycrystalline, where you get to see many crystals. Many. Poly means more than one. As long as you have 2 or more, is poly already. So 2 or more is poly. If you have a single crystal infinitely, that is called mono. So that already tells you what you should expect on XRD. So the moment you have more than one crystal, you should be able to see more than one peaks on the XRD. So one peak belongs to one crystal. For example, silicon, you might see one at 69 degree, your 2 theta 69 degree belongs to one peak. So if you see the second one, for example, at 20 something or 30 something, it could belong to another peak as well. So in that case, if you have poly, you should be able to see more than one XRD peaks. Okay. Ada lagi tak other than XRD, any other method that you can use to complement the result for polycrystalline? Any other? Anyone done Raman before? You can also use Raman, okay? if you use Raman on monocrystalline, you have to see a peak, a very sharp peak, small FWHM means dia punya full width half maximum tu, dia punya lebar tu dekat 50% of the height is very thin and very sharp needle lah. Sharp needle, dia bukan broad. It's very sharp needle. If you see that single peak at 521 centimeter minus 1, then that belongs to monocrystalline silicon. If you see anything lesser than that, for example 519, 518, 517, that's highly polycrystalline. If you see a broad peak at 480 broad, there's no needle, it's just a broad at 480. So that's amorphous silicon. So amorphous 480, polycrystalline onwards. If you see one peak at 521, it's monocrystalline. So that's how you can see the evolution of the silicon depth. So that can be done for spark silicon, evaporated silicon, or some other methods to deposit silicon as well. Okay, so that's beyond deposition. So that's a bit on the characterization, and that's how you can verify the quality of your films, because it goes back to the deposition temperature here. By default, when you do your deposition at a very low temperature, for example at room temperature in some systems, then normally you will end up with amorphous silicon. So if you increase your deposition temperature 200, 300, 400, 500, up to say 1000 degrees C, then the film quality tends to be higher in crystallinity. So you may have polycrystalline or higher polycrystalline, a bit of amorphous, completely monocrystalline, but just a little bit of amorphous, or maybe highly monocrystalline, but some regions are still poly or perfectly mono, right? So that is the effect of your deposition temperature. So you can verify that on the characterization like Raman and XRD. So this is the use of your previous FYP knowledge. Okay, so another system is high density plasma CVD. So bias can also be applied. So room temperature, you can do the deposition temperature at a very low temperature. Okay, it's called high density plasma. If you see the supply here, the electricity supply based on microwave, it can go up to 2.45 gigahertz, but this is not what we call a common system. The most common system that we can see in industry is LPCVD and PECVD, right? If you talk about in Silterra, then we have a couple of LPCVD systems, right? If you talk about, I think maybe PECVD system as well. If you talk about solar cell manufacturing, then PECVD is used for silicon nitride anti-reflective coating deposition, thin layer. But other like other CVDs are not common if you're talking about these two industries, at least. Another LACVD, laser assisted. So you do the decomposition as well. So the basis remains the same. You still have to have decomposition of your precursor material to enable deposition. It's just that you have different methods of CVDs in order to do different sort of decomposition. So in this case, it's a decomposition by laser, just now decomposition by plasma, or the default one is decomposition by high temperature. So, but in the nutshell, you have to do, you have to have thermal, you have to have decomposition of the precursor material to enable deposition. Okay, so this one is laser assisted. This one is not common because laser itself is quite expensive. And if you talk about laser, it's hard to have what we call a scalable laser system. When I talk about scalable, I mean is it's compatible to the mass production. You may use laser system with small laser beam in the lab, but if you want to scale that the very same laser beam to a very big size so that you can do CVD for a big sample, then it could be a bit difficult because scaling up laser that we need to use a laser system or laser illumination with a big size or over a big size, and that will be more costlier, right? But we can do this, but it's just that whether it's scalable or not. So when I talk about scalable, one more thing, whatever you learn in the process is the fundamentals of how do you do the fabrication. But whether or not the process is scalable to certain industries, so that is another factor to be considered. So you may learn many MBE or what else? Lithography, like beam lithography. Then we learn about MBE, molecular beam epitaxy in thin film deposition to do epitaxial deposition. But these two systems are very good at the control of the process. So when I talk about process control, they are superb, they are very good, but then they are not feasible for mass production because they are just too slow for mass production. So if you compare EBL, for example, with projection optics like scanner, ARF, EUV, EBL is way slower than a compatible system. So some systems that we learn are not compatible, but they are okay for the lab use, but they are not for the industrial application. MBE is another system. It's very good at process control. You can control at a very layer level, atomic kind of deposition level, but then it's too slow for mass production. So that's why If you talk about nitride deposition, nitride preparation, fabrication for LED industry, then MOCVD is more preferred, for example. So that's why you see OSRAM use CVD to do the nitride deposition. So that's another factor that you have to bear in mind. So everything that you learn can be applicable for mass production due to some factors. Right, step coverage we've learned about step coverage in PVD when we learn about evaporation, when we learn about sputtering. We have evaporation is worse as far as step coverage is concerned, and sputtering is always in the middle, and CVD is always the best, right? If you talk about the CVD system alone, then there are a lot of factors that can affect step coverage. For example, if you talk about pressure, if you go for high pressure, then we've learned last time in vacuum technology that you're going to end up with shorter mean free path, or MFP, or lambda. So if you have high pressure for your CVD, then you're going to have your lambda to be small, and that may affect the film quality as well, and the step coverage, particularly if you have features, existing features on the sample, or on the existing that you're going to cover by CVD. If you talk about conformal, then we're talking about equal film thickness over all sub. It's very easy to do on planar substrate, or on planar films, or planar existing films. We're going to see later on when we talk about process integration, that we're going to multiple processes together enable the device fabrication from day 1 until day 60, for example. So it's going to be challenging when we're talking about features, particularly small features, particularly when we're talking about small technology nodes, when you want to ensure good step coverage, particularly in the trenches, it's going to be very, very challenging. So you need to really look into the process optimizations in order to enable good film quality and film coverage. Right, high surface diffusion. You want to have high surface diffusion. So this means that whatever you have, when you have your films or your atoms or your molecules deposited on the layer, on the existing layer, on the substrate, you want them to have a high surface diffusion. You don't want them to just land on the substrate on that particular location and stop. You want them to move a little bit to settle down, to find the best position, for example. Low sticking coefficient, more desorption, redeposition. Non-surface, non-conformal coverage, on the other hand, low surface diffusion. Atoms landed right there and then, and there's no more movement. So it's called low surface diffusion. And film topology depends on arrival rate and arrival angle, of course. But we have discussed last time that CVD has omnidirectional deposition. So that means the deposited atoms will be coming from. So you have features on the layers or on the substrate. For example, last time when I talked about my previous PhD on textured glass, where I have all these features at steep angle. So I normally have good deposition on this area, but I have bad deposition in the valley normally. So this is what I want, the thickness, but I end up with a very thin one in the valley due to lack of omnidirectionality. But this, the very same glass substrate or textured substrate, other textured substrate, silicon or whatever, if you go for CVD deposition, it will guarantee you a more uniform deposition in comparison to CVD. So you will end up with more conformal coverage and better conformity across all substrates, right? Particularly if you have structures like that on top. Okay. So next, so this is what I mean. If you have rapid migration, no migration, or no migration. So if you have migration here means I'm surface diffusion. So you have diffusion across, so that means it will smoothen the layer form, so near the trench. On the other hand, if you don't have any surface diffusion or low surface diffusion or no surface migration, you'll tend to end up with swollen features, more or less. Okay. Particularly with trench area with high aspect ratio. Okay. Trench area, high aspect ratio. So you're gonna end up with that, shoulders or swollen features if you like. Okay. So trench is the hardest one. Dekat any area yang atas tu, it's not a problem. Oh, finished already. So done CVD. Okay, let's just continue then to process integration. I have 77 slides, but it's quite straightforward. Okay, let me just continue to process integration for maybe 15 minutes. So I've just uploaded this on eLearn before the class. The slides on process integration. So I'll just go right into process integration now. Hold on, let me. Okay, can you see the slides on the process integration? Okay, that's good. So if you are called by Silterra, for example, to join one of the departments, so it's about process integration. So that department is called Fab integration, right? Fab integration is doing something that I'm going to talk about now. Okay, so it's called process integration. So when I say it's process integration, so I'll just skip this. Later on, you go through the questions yourself. So it's about combining all the processes, all the knowledge that you have from previous processes to do complete device fabrication, to enable complete device fabrication. Sebab kalau kita nak fabricate kita punya device, IC ke, solar cell ke, solid state drive ke, whatever, whatever it is, you always need to integrate different processes in order to produce the final product. Okay, so the process sequence and the process parameters and the setting, the equipment may be different from device to device, from model to model, from industry to industry, but it's about combining all the processes that you have, or most of the processes that you have, in order to enable device fabrication. So process integration is the combination of all semiconductor fabrication processes in appropriate sequence to fabricate the whole stack of CMOS transistors. So now we're talking about IC fabrications, then we're talking about CMOS in particular, but the basics apply to all other devices as well. So we have learned from the fabrication of the silicon wafers, and then we start off with thermal oxidation, lithography, etching, diffusion, implantation, film deposition, until today, right? So we've covered pretty much everything that you have to know in the fabrication process. So we're going to combine, we're going to learn how do we combine. All right, this is what a simple CMOS looks like. It's just a simple one. So let's recap on what we've learned so far before we move on to every single process that will prepare the fabrication. Okay, we start off with the wafer. So you know the wafer preparation already. So I'm just going to draw here more or less. So this is the wafer. So you may have normal wafers or epi wafers. So in this case, the example is using epi layers on the wafer, P minus and P plus. So you have learned about the doping already. How do you get P minus? What is the level of P minus? What is the level of P plus? What do you need to do in order to get your P plus? So done. You already know wafers. And then at the bottom part of this CMOS, okay, so I can divide here, and I'm going to show you something here. I'm just going to slash this one into two parts. Part one is down here, and part 2 is up here. Okay, so what is part 1 and part 2? When you go into a wafer fab in particular, so they will call this part 1 and part 2 as front end and back end. So kita dah discuss dulu ni, when we talk about the industry, semiconductor industry in particular, then we always refer wafer fab as the front end and the packaging assembly as the back end, right? But in the wafer fab itself, we also have front end and back end of the fabrication process in the front end industry. So we even have front end and back end within the front end industry. Okay, so front end is normally called FE to front end, BE is back end. Kalau you masuk wafer fab, then this is the term that you will always hear, front end, back end. In fact, kalau you join process integration department ataupun fab integration, you will either be assigned to do front end or back end. So you will be attached to a front end process integration engineer or back end process integration engineer. So it's not possible to do, well, in the short run, it's not possible to do everything. You don't have time to cover front end and back end in your daily job because it's just too much. So because you're talking about process cycle of like 2 months to 3 months, so the front end may take 1 month, 1.5, and then the remaining 2 months or the remaining 1.5 months could be on the back end. So the whole flow in the front end, from the thermal oxidation, the very first one, the PADOX, until you have your polysilicon here, that I divide into the first part here, is already a lot to cover. Okay, so if you see in the first part here, you have silicon wafers, you have gate oxide, you have diffusion of your source drain, you even have your well. It's not only the source drain on the left and right, you may also have your well that is fabricated by implantation process, for example. So now we're talking about having source drain in a well. So that itself is already complicated. And then you have your contacts, you have your spacer nitride. I'm going to go through one by one later on, don't worry about it, until your polysilicon. So that is so this one is the gate. Yang atas ni gate. Selama ni kita nak discuss gate oxide, and then your source drain, and then your wafer. That's it. As simple as that. But this is more or less real life example, but this is still a very example of the real device. Okay, so that is the first part. It's called front end, and another part number 2 is called back end. So back end ni akan start bila you start to fabricate your metal contact. So this metal one is your first metal layer. So we're going to cover the details of the metal and connection in the lecture after this topic, in the interconnections and contacts. How do you choose your metal? What are the issues with metal? What else do you have to know about the metals and stuff? So you can see here on this simple representation, you have metal 1 and then you have metal 2, right? Then how do you connect your metal 1 and metal 2? You have to connect the metal 1 and metal 2 by a via, called a via. Via tu lubang, hole. Macam telaga lah, macam trench. Tapi normally we call trench for the front end, STI, shallow trench isolation and stuff. But when it comes to the back end, we don't call it trench. We call it via. Okay, so this is a via, this is a via, this is a via, this is a via. Okay, lubang. So dalam tu kita akan connect metal contact. We call it tungsten via plug. Plug tu macam contact lah, macam you ada metal 1 kat sini, then you have to, I'm going to show you layer by layer processing later on. You're going to dig a hole, so that is called via, and then you're going to deposit tungsten, guna firm deposition. You deposit tungsten to produce a plug, then you deposit metal 2. Then you're going to have next layer. So this is only like 2 metal layers and done. You have your bond pad already. So bond pad is the finishing lah. Then that's the final contact that you will probe your device later on for the measurement. So now, when I left Sutera last time, I think Sutera had 2009, there was already metal 6, until up to metal 6 more or less. up to metal 6. Then after metal 6, then you're going to have your top metal. So that means if you look at this configuration, we're talking about metal 1, VR1, metal 2, VR2, metal 3, VR3, metal 4, VR4, metal 5, VR5, metal 6, then metal 6, VR6, top metal. So you're going to look into the cross section later on. Itu saya pernah bagi cross section VSAM of typical CMOS device dalam WhatsApp group. So if you can revisit that, you can see metal VR, metal VR, metal VR sampai habis. So that is already a lot. So that's why you're gonna have front end as one group taking care of the whole processes on the front end, and you're gonna have like back end as another group taking care of all the processes, metal VR, tungsten deposition, IMD and stuff, up to the bond pad deposition. So kalau you masuk Silterra or Infineon, I'm not sure about how the category looks like because they are doing power devices for automotive applications. So the configuration is different. So therefore the complication is also different. So if in Silterra you're talking about polysilicon gate width of about 100 nano, then in Infineon you're probably talking about gate width of 1 micron. So because the application is different, so the gate width and all other device configuration will be different as well. And it's a lot easier for me, I think, as a litho guy last time. It's a lot easier to do 1 micron fabrication process in terms of process control, process sustaining, process improvement, in comparison to CMOS with 100 nanometer as far as process control and sustaining are concerned. Okay, so let me see. Okay, so I can go through this slide as the last slide, then I'm just going to stop. Then we're going to continue next Monday. Okay, so when you talk about process integration, so on this, we can divide this device structure into few modules, few parts. Okay, sebelum ni kita tak ada sebut apa-apa lagi. So now you can see that you have many things: metal via passivation, silicide, wells, source drain, silicon. So how do we divide all this? So we can divide all this into few groups. We call it isolations. We're going to see later on what is isolation, how do we fabricate isolation, how do they function, and then we have wells as a second one. Wells, so you have seen the P well, N well, and stuff. So there'll be adjacent wells as well as you talk about the whole structure in the wafer. And then you have junctions. We have learned about PN junction basics. So now you can see that you have P plus, P minus, PN junction. You even have like P minus, P plus junction as well. So bila kita belajar 386 tu, saya dah ajar kan, saya sebut junction is not always about PN junction. It can also be P plus. It can be also from P to P plus, NN plus, P minus, P plus, P minus. As long as you can see variation in doping levels that are obvious, so that is called junction already, right? So you're going to cover junctions. So you're going to cover gate stacks as well. So you can see polysilicon gate here, and then the gate aux, so that is considered gate stacks. And the final one will be interconnects, where you are looking at metal, tungsten, VR, and all those stuff until the final device, right? So in the next few slides on Monday, I think I can finish that on Monday. We're going to look into all this stuff. How do we go into all the processes from the very first step, from this step, pad aux preparation by the thermal oxidation process, and then we're going to build the layer until you get the whole device for process integration. Okay, so that's all from me. Do you have any questions? So that's the intro of process integration. Anything? So more okay so far? Any questions on CVD or process integration before your new year? Just gonna stop sharing now. Okay, so far okay. All right then. If there's no question, then I'll see you Monday next week. We're gonna finish off with the remaining of process integration. Then inshallah on Tuesday we're gonna go through metal interconnection and metals and interconnects. Then yeah, that's all. So I'm gonna give you assignment 1, I think, over this weekend. Right? I'll let you know in the group later on. So we have few more weeks to go. Now it's 12, 13, 14, 15. So we have 3 more weeks to go. So I'm going to give you your assignment 1, and then your presentation, and then eventually the test number 2. So it's going to be a bit packed towards the end of the semester. Okay. Kalau tak ada apa-apa, that's all from me. So happy New Year 2021. So inshallah, hope for a better 2021 in terms of our learning experience, in terms of pandemic. Hopefully everything gets better, and everyone please stay safe on the eve of New Year. Okay, so make sure you stay safe and observe all the SOPs. Right. So that's all from me. Bye bye. Take care. Assalamualaikum. Stay safe. Happy New Year. Bye. See you Monday. Okay.